and welcome to Activity 29. Today we are starting with Lesson 29.1 on page 393 in your Springboard textbook. Today we are going to be talking all about polar graphs and comparing and contrasting polar graphs and comparing them with the rectangular equations. So polar graphs have a bunch of different types of shapes, and these are some common ones that we will investigate as the activity goes on. But basically with a polar equation, it's in terms of r and theta. So when we talk about a rectangular coordinates, if you look at your graphing calculator and you look at the y equals menu, you have x's and y's, right? Everything is in terms of. With polar equations, it's back to being in terms of r and theta. Now on your graphing calculator, to put something into the correct polar mode, you go under the mode menu, and you scroll down to this piece here where it says function. Functions are normal mode, but we do have a polar mode on our calculator. So if we hit enter on that and then quit out, now if we go into the y equals menu, we see that we have this in terms of r. And when you type in, instead of seeing x, you'll see the theta. So that's how we turn this into polar mode. So mode and then polars instead. Okay. Now, if we type in, if we look at the first number 1, it wants us to investigate the polar equation r equals 3. So if we just zoom 6 here, what we're seeing is we have a circle, although it doesn't kind of really look like it. It kind of looks actually a little bit less circular. So maybe do like a zoom 0. It kind of looks more like an ellipse, but it's because of the scale on the graph. If you look here again, it's a circle. It's centered at 0, 0, and the radius all the way around is 3, right? So whether you look at the zoom 6, zoom 0, one of the two, you'll see that circle with a radius of 3. So again, it's a circle. We're going to write down some characteristics of this. Its radius equals 3. Center is at 0, 0. And again, if we graphed this on the rectangular plane, it would look like this with that center and then points all the way around. Here's our rectangular, okay? Now, to write this in rectangular format, we know that when it's centered at 0, 0, x minus h quantity squared, y minus k quantity squared equals your radius squared, right? So there's the rectangular formation of this particular one. Now, if we wanted to convert this, though, thinking back, remember, we know that officially we have the square root, r is equal to the square root of x squared plus y squared. Or another way to write that, if we squared everything, this would cancel out, and we're left with r squared equals x squared plus y squared, right? And that's what they're getting at over here. It's kind of two different ways to think about your r value, that substitution, either r equals square root of x squared plus y squared, or r squared equals x squared plus y squared. So since the r is 3, r squared is 9. So we kind of see that difference between here, plugging that in for our equation to get the conversion between the two, okay? So basically what we're seeing when it comes to polar equations, anytime you have a polar equation in the form r equals a, it's always going to be centered at 0, 0, and then your radius is always the a value, so it would be equal to the a squared. So there's kind of a direct conversion between those, okay? Now, if we were checking out these other graphs, so I have these other graphs of r equals 3 cosine theta, -4 cosine theta, and 1/2 cosine theta graphed here, we see that these are again circles, although our graphing calculator makes them look a little disoriented. We see that these are all still circles. Now they're just shifted along the x-axis. So now notice it's the whole diameter is 3, whole diameter is 4, shift to the left now, or the diameter is 1/2, okay? So notice these are all along the x-axis, but they are different diameters, okay, and shifted different directions. So without graphing r equals 2 cosine theta, some things that we could probably say about this graph without even graphing it is that we know that it's going to have a diameter of 2, right? We're noticing this, there's a correlation between the diameter and the leading coefficient here. And we notice as this is positive, it's going to be shifted to the right. And so the center would be at 1, 0, right? Because we're shifted to the right. And if the whole diameter is 2, the center would have to be at 1, 0. Now, we can obviously test this out by graphing it and looking, okay, if we take 2 cosine theta and look at it in the calculator, all right, we can confirm that center is at 1, 0, diameter is 2, radius is 1. You see that piece there. And again, shift it over all the way around here to actually officially graph it. Okay, so what we're seeing whenever you have this this A cosine, the A value, the absolute value of it, is going to be equal to the diameter value. And then if it's a positive value, it's going to be shifted to the right. And if there was a negative out front, it was shifted to the left on that x-axis. Okay, so when we switch this up and talk about a sine graph, it's going to actually kind of be prediction-wise a similar thing. The A value is going to be the diameter, again, the absolute value of A, and then this time a positive value is going to shift it up, a negative value will shift it down. Okay, and we can confirm that if we just check this out. If we go look at this graph again and we type in a sine as opposed to the cosine, we see it being shifted up, but again, that diameter of 2, radius of 1. Now we're at 0, 1 as our center, and shift it up. So as we start looking at these, just looking at different equations, if we start by the center one here, notice we're centered at 0, 0, so we know this is just an R equals, and our radius this time is 4, so we're just R equals 4. Now to shift this up, okay, we're going to shift this around a little bit because remember that means we're going to make it an R equals something sine theta. And in this case, it's equal to the diameter, which if the radius is 4, the diameter is 8. And then our last one would be shifted down. So that would now be -8. Oops, not cosine, sine, since again we're shifting down versus left and right. Okay. And if we converted these to rectangular then, all right, again, we're kind of thinking back to what we know this means. If we're centered at 0, 0, we have x squared plus y squared equals r squared. If we are shifted up, our center here is now at 0, 4. So x squared plus y minus 4 squared, and then equals the radius squared, which is 16. Versus our one that was shifted down, whose center's at 0, 4. So x squared and then y plus 4, when we plug in that h, equals 16. Now we did actually talk about converting these the last lesson, using, the square, making that substitution in for r, and then how this was would be for sine would be y over the square root of x squared plus y squared. But we can also, especially when we're given a picture, understand how we did last unit, writing the equation of a circle and seeing that connection between the two. Now, we also have a graph, what we notice here for the equation theta equals 45. So if we keep typing in, no matter what r value, if theta equals 45, no matter what the r value is, what we're saying is it always equals 45 degrees, right? Theta is consistently 45 degrees. So as we start graphing this, we're at an r value of 1 and 2, 45, and then we're at -1, 45, which is really if we add 180, 225, and same thing with 3. So basically what we're seeing here is we're actually graphing a line, right, on here. And in fact, this line, if we think back to the coordinate plane, we're rising 1, running 1, rising 1, running 1, rising, running. So if we converted this to y and x, it would just be the slope of a line with a slope of 1, right? Now going back to actually why does that work out, think about what we've talked about with theta, right? We've talked about how tan theta equals y over x. So if we plug in, if we know we're dealing with theta equals 45, and to make this into tan theta, both of them have now a tangent. Tangent of 45 is 1. And again, we can make this substitution for tangent of theta, that it equals y over x. Multiply both sides by that x, we get y equals 1x or y equals x. Okay, so we can kind of confirm what that prediction was about our slope. So same kind of idea with when theta equals 60. Essentially what's happening is we kind of have another line, this time going through 60. And again, if we think about converting this, if we turn both of these into tan thetas, or tan 60s in this case, tangent can be substituted to be y over x. Tangent of 60 degrees is the square root of 3. So we can predict that this is now a line with the slope of square root 3, which again we kind of see happening here moving on. Okay. All right, we're going to work more with this in class. Thanks for everyone for watching, and have a great rest of your day.